Welcome to the projectile motion video. So anything that is flying through the air can be considered a projectile, as long as it's the only forces acting on it are the forces of gravity that are pulling it back down to the ground. So the only acceleration it's experiencing is a vertical acceleration pointed towards the surface of the Earth, equal to 9.8 meters per second squared in our case, or depending on where you are on Earth, it could be slightly different than that. Okay, so defining a projectile, we can say a projectile is free fall motion. Okay, that's kind of weird because we talk about free fall like straight down, and projectiles have velocity in two different directions. Okay, they have a component, a vertical component, and a horizontal component of their velocity. But it's similar to free fall motion, but the object was launched with an initial velocity, so it has both vertical and horizontal components to its motion. Okay, so the ball is launched, okay, and it has both a vertical and horizontal components. It's changing its position in two dimensions, okay? So this is the first time we're looking at situations like this, where there is a change in motion there's a change in position in two different dimensions. Okay, for projectile motion in this class, we are going to assume that there's no acceleration in the x direction, that the only acceleration experienced by that projectile is in the y direction. Typically, we're going to call the y direction, the upward direction, to be the positive y, and I have shown that here in this reference frame. So in this case, the y acceleration would be negative 9.8 meters per second squared. Okay, so you can have like an object like a tennis ball flying through the air, or a golf ball, or something like a marble, or you can look at modeling something like a person jumping off the ground and model their center of mass, and you would find that once they leave the ground for a jump, their center of mass follows the path of a projectile. Okay, or we see the water here in this fountain follows the path of projectile, or the lava here. So we see this everywhere, this type of motion. So projectile motion is in two dimensions. I've been saying this, but let's look at this in a little bit more detail. So we're saying, for example, let's say that there's a basketball thrown up to the east. Okay, so you shoot the ball or you throw it up in the eastward direction and kind of upward, as shown here in the diagram. So at each point along this trajectory, the ball is experiencing an acceleration on the like up-down axis of g, pointed straight down back towards the ground. Okay, so 9.8 meters per second squared is the acceleration that it's experiencing in the vertical or up-down axis. Okay, but the north-south axis, we have no acceleration. So if this ball is thrown directly east, it has some up-down velocity initially, some east-west velocity initially, but it has no initial velocity in the north-south direction. As long as there's no north-south acceleration, which there's usually not, then the ball is going to stay in a vertical plane that's oriented east-west. Okay, so as soon as you let that ball go, it's not always an east-west plane, but that motion of the ball is going to occur in a plane, or motion of the object is going to occur in a plane. So we have two-dimensional motion. Okay, so let's look again at like an example of a basketball being shot. So when we set up a reference frame now for a projectile motion problem, we need to set a 0 point. When I go down there, okay, we need to set a 0 point and then also like a positive x and positive y direction. So now we know the sign of g. So if we've set up a reference frame as shown, our acceleration of gravity is going to be a negative g, or negative 9.8 meters per second squared. And our acceleration in the x direction, once that ball is accelerated and you've thrown it, okay, once it leaves your hand, there's no horizontal acceleration. Okay, remember, we're assuming there's no air resistance, so there's no acceleration in that x direction. Okay, so remember, an initial velocity is going to be a vector, so we could explain that initial velocity of the basketball with a magnitude and direction. So we could say the vector v has a magnitude v naught, and it's in the direction theta above horizontal, theta degrees above horizontal. Okay, or we could split that vector into its components. Okay, an initial y velocity and an initial x velocity using trigonometry. Okay, it turns out that that's super helpful to work with the components of the velocity, because that x component of the velocity, there's no acceleration in the x direction. So that x component of the velocity is going to be the same throughout this projectile's path. Okay, throughout all the motion when it's in the air, that initial velocity that you calculate right there is going to be its velocity in the x direction. Okay, we can look at this closer if we follow. Okay, so the ball comes up and it's reached its highest point in its trajectory. Okay, we saw with free fall that at the highest point in a ball's trajectory or an object's trajectory, that y velocity is 0. Okay, same thing with a projectile. Okay, when it reaches its highest point, the velocity in the y direction at the top is 0 meters per second, right? This is the point where its velocity is switching from being positive to then it's going to be negative because it's being accelerated back towards Earth. Okay, so it had a positive velocity initially. That positive velocity decreases until when it reaches its highest point, it's 0. And then its y velocity is going to be negative for the remainder as it's coming down, for the remainder of the trajectory path. Okay, but that velocity in the x direction at the top is going to be that same velocity that we had down here that we solved for with this initial velocity, and that's because we have no acceleration in that x direction. Okay, if we were to continue and look at the ball has now come down, when it's reaching the hoop, it has some negative y velocity. Okay, now pointed in the negative direction, and I haven't put the negative sign on there, but you do see the arrow. So the arrow shows you that it's negative because it's in our negative y direction. Okay, again, we could describe this in terms of its components, this vector v at the hoop. Okay, we can describe it in terms of its components, or we could talk about the magnitude and direction of that velocity vector. Okay, so like I was saying, the vertical component of the basketball's velocity changes. It's initially positive, then there's a point at its highest point, it reaches 0 meters per second for its y velocity. Okay, and then its y velocity becomes negative as the ball starts coming back down. For the x velocity, the initial x velocity that the ball is given, that x velocity is going to remain throughout that trajectory. Okay, and that's because we don't have any acceleration in the x direction. Okay. Okay, so looking at that, we kind of start to realize, well, our x and y components of our velocity and the x and y components of our motion, it looks like we can kind of treat them separately. We can talk about the x velocity kind of not changing. In the x direction, it has a constant velocity. In the y direction, it has an acceleration of negative g. So that's actually the case. The vertical and horizontal components of motion are independent of each other. Okay, a good example, a typical example of this is to look at like an object. So we'll say we have two tennis balls. This green tennis ball is just going to be dropped. Okay, but another like yellow tennis ball here in this picture is going to be given some horizontal velocity to begin with. No vertical velocity, not up or down, just some horizontal velocity to begin with. I guess they're going to be thrown this way. The other one will be thrown that way. Okay, so as they're thrown, if you were to take a snapshot every, like, I don't know, half a second, okay, and were to track the motion of these two balls if they were released at the same time, you would find that their horizontal is different, right? The yellow one has some horizontal displacement, whereas the green ball is staying in the same horizontal position, but their vertical displacement is going to be the same, okay? So if you were to track both of those, you'll notice that they go down vertically by the same amount, or they have the same displacement every time point, okay? So basically, the two balls, since they both have the same initial vertical velocity, which is 0 for both of them, the green one is dropped, and the other one is given a horizontal velocity, but no vertical velocity. So they're both on Earth, we're assuming, right, and have an acceleration of negative 9.8 meters per second squared. So the vertical component of their motion is identical. Okay, the vertical component is identical. It can be treated pretty much like a free fall problem if you're just looking at the y component of the velocity, okay, or the position. It's kind of independent of that x velocity, that initial x velocity that you gave it. Okay, so when we go to solve projectile motion problems, and I'm going to post, it's actually not my video, but it's a good video that goes through and gives kind of some examples of projectile motion, and then also works you through some example problems. She's much more entertaining than I am too. She does a great job with her videos. So I have another example video for you to go through and look at examples and practice problems. But the equations that you're going to use for projectile motion are almost simpler than the ones that we've been looking at. They're the same, but you can simplify the horizontal motion because we don't have any acceleration in the horizontal direction. Vertical motion, it looks very similar to our free fall problems. Okay, because the acceleration is g, and a lot of times that's going to be negative g, right? If you call vertically upward to be the positive y direction. Okay, so for horizontal motion, we have that the initial velocity is going to stay the same throughout. So if you're looking for the horizontal velocity of that object at any point throughout its trajectory, that horizontal velocity is going to equal the initial horizontal velocity because there's no acceleration. Okay, for our y direction, that vertical component of the velocity, that you can get by using our equation Vy equals V naught, the initial y component of the velocity, plus g times t. Okay, remember sometimes, depending on your reference frame, you might have to turn this into a negative g. Okay, and finally, the position versus time equation for projectile, looking at its horizontal and vertical components. Your horizontal component of the position is just the simplified or special case of like constant velocity motion, where we say position is equal to the initial position plus the velocity, the initial velocity times the time. Okay, because that velocity is not changing. We have a simple equation to tell us the horizontal displacement of the object as a function of time and the initial velocity. In the y direction, the equation is a little bit more complicated, but it's the same one we've been working with, where our vertical position equals the initial position plus the initial vertical velocity times time plus 1/2 gt squared. Okay, so these should look familiar. And basically when we do projectile motion problems, you're going to split the initial velocity that you're given into its horizontal and vertical components. Okay, you're going to solve those equations for horizontal and vertical, and a lot of times you can figure out a time, and the time is what connects those two. So I'm kind of rambling here, so I'm going to end the video, but go ahead and go watch the other video that I post. Has good examples of projectiles, and she works through a couple problems too that I would like you to get in your notes. Okay? So thanks for watching. I hope this was helpful.